Imagine a product where, like, the more expensive it gets, the more people rush to buy it. And I mean, I am not talking about a luxury sports car or, a designer handbag where the massive price tag is basically the whole point. I am talking about a situation where the buyers are completely desperately poor, the product is an absolute basic necessity, and a price hike actually forces them to consume more of it.
Right, yeah. It sounds like a literal glitch in the economic matrix. I mean, it directly violates the fundamental law of demand that we're all taught on day one.
Exactly. It completely breaks that intuitive rule that higher prices mean lower demand. But it is a real phenomenon. It's an extreme mathematical paradox known as the Giffen good. And understanding exactly how and why that paradox happens is, well, it's the key to unlocking the deepest levels of microeconomics.
Which is precisely what we are dissecting today. Welcome to the deep dive. For you listening, we know exactly what your mission is right now. You are staring down the barrel of the Indian Economic Service exam, specifically the GE-01 paper for your master's level revision. And you are tackling Consumer Demand Theory, Part 1, focusing on utility and demand derivation.
Yeah, and we have gathered a literal mountain of dense academic sources, textbook chapters, historical economic papers. But look, we're not going to just read a table of contents to you. We're going to build this entire architectural framework around the actual hurdles you have to clear. So we're grounding this session by locking on to 3 landmark IES previous year questions that basically form the structural backbone of this entire field.
Because if you can master the mechanics behind these 3 specific questions, you have effectively conquered the core of consumer demand. So the first is the 2025 question, which requires you to define the marginal rate of substitution and actually calculate it for a Cobb-Douglas utility function.
A heavy hitter for sure. And the second is the 2024 question, asking you to state, prove, and derive the demand curve for that bizarre Giffen good we mentioned using Slutsky's theorem.
Right. And finally, the 2023 question on checking the consistency of a consumer's behavior against the axioms of revealed preference.
Because when you sit down for the GE-01 paper, the examiner isn't going to ask you to just write down a textbook definition. I mean, they are going to hand you a mathematical function, a budget constraint, and a price shock, and they fully expect you to find the exact numerical split of how the consumer reacts. So our roadmap today is causally linked. We have to start inside the consumer's mind, to understand how they value anything at all.
Right. And once we have that utility, we basically give them a budget and watch them make a choice. And once they're comfortable in that equilibrium, we shock their system with a price change to see the chaos of the income and substitution effects. And finally, we just reverse engineer the whole thing. We look at the hidden mathematical mirrors called duality theory and revealed preference.
It is a perfect logical progression. We're building the consumer from the ground up, constraining them, disrupting them, and then mathematically proving their behavior. So let's start with the foundation, which is value. Before we can even draw a demand curve, we have to quantify desire. And this drops us right into one of the most famous historical debates in economic thought, the battle between cardinal utility and ordinal utility.
Yeah, this is the critical transition from classical economics of the late 19th century to the modern microeconomics we actually use today. So Alfred Marshall and the early Marshallists, they championed cardinal utility. They operated under the assumption that utility, which is just the satisfaction you get from consuming something, could be measured in exact, absolute monetary terms, or in these hypothetical units they literally called utils.
Right, so if I eat a slice of pizza, Marshall assumes I have this internal meter that definitively says, that slice yielded precisely 15 utils. And if I eat a second slice, maybe it only gives me 10 utils.
Exactly, which introduces the bedrock concept of the law of diminishing marginal utility. So as you consume consecutive units of a specific good, your total utility increases, but it increases at a steadily decreasing rate.
So, the first slice of pizza is a revelation. The second is great. The 5th slice makes you actively reconsider your life choices.
Precisely. The marginal utility, which is the derivative of the total utility function with respect to quantity, goes down as consumption goes up. And Marshall used this physiological reality to explain why demand curves slope downward. I mean, you will only willingly purchase that second, less satisfying slice if the market price drops to match your lowered internal valuation.
That feels incredibly intuitive, honestly. But Marshall built a trap for himself, didn't he? Because to make the math work, to measure utility using money as the yardstick, he had to make a massive fatal assumption.
He did. He assumed the constant marginal utility of money.
And why is that a fatal flaw? I mean, inherently, a dollar is a dollar, right?
Well, a dollar is a dollar in nominal terms, sure. But its utility is highly subjective. If you use money as a measuring stick for human happiness, the measuring stick itself cannot shrink or expand. So Marshall had to assume that whether you are dead broke or a billionaire, finding a $20 bill on the sidewalk brings you the exact same amount of psychological utility.
Oh, which is completely divorced from human reality. If
Yeah.
I have $10 in my bank account, spending $5 on lunch is an agonizing financial sacrifice. Like, the marginal utility of those remaining $5 is astronomical, but if I am a billionaire, spending $5 million might go entirely unnoticed. The utility of money absolutely diminishes the more of it you accumulate.
Exactly. And if the measuring stick is changing its size depending on the wealth of the person holding it, you just cannot build a rigorous scientific model with it. Cardinal utility falls apart under its own weight because it relies on that absolute measurement.
It also runs into a massive philosophical wall when you try to compare two different people. Like, if we both eat the exact same pizza and I say I received 20 utils and you say you received 10 utils, does that scientifically prove I enjoyed it exactly twice as much as you?
It does not.
Not at all.
Right, because maybe my internal scale is just dramatic. Maybe my 10 is your 100. There is no objective scientific way to compare my subjective experience to yours. Interpersonal utility comparison is basically a ghost hunt.
Which necessitated a total revolution in economic modeling. Enter John Hicks and Roy Allen in the 1930s. They introduced the ordinal utility approach. They realized that for demand theory to work, we do not need to know exactly how much you like a good. We don't need a psychic thermometer. We only need you to be able to rank different bundles of goods in a consistent order. It's the difference between asking someone to rate a movie exactly an 84.3 out of 100 versus just asking them if they liked it better than the movie they saw last week. Ranking is something human brains actually do naturally. I prefer an apple to a banana and a banana to an orange. I don't need to assign an arbitrary numeric value to any of them to make that choice.
And that shift is everything. Ordinal utility requires much weaker, vastly more realistic behavioral assumptions. You just need to be able to say bundle A is preferred to bundle B, or bundle B is preferred to A, or, you are perfectly indifferent between the two. The impossible interpersonal comparisons just vanish. We only care about your internal hierarchy.
But if we throw away the absolute numbers, how do we visualize this hierarchy? Because we cannot just hand an examiner a list of a billion possible combinations of groceries. We have to draw a map. And that map is built entirely out of indifference curves.
Right. So an indifference curve is the visual representation of ordinal utility. It is a mathematical locus of points combinations of two goods that yield the exact same level of total satisfaction to the consumer. Because the utility is identical across all these combinations, the consumer is indifferent to which specific bundle on that curve they actually consume.
Let's assume we are dealing with two normal goods. The classic textbook example is usually something like clothing and food. The curve, representing a single level of utility, bows inward toward the origin. It is strictly convex. Why the bow? Like, why not just a straight diagonal line?
Because that convexity is the visual proof of a diminishing marginal rate of substitution. If you have a massive wardrobe of clothing but you're starving, so you have very little food, you will gladly trade away a huge amount of clothing to get just one loaf of bread. But as you slide down the curve, as you acquire more bread and lose clothing, bread becomes less scarce and clothing becomes more precious.
So my willingness to trade changes based on my current inventory.
Exactly. When you have 10 loaves of bread and only one shirt left, you are certainly not going to trade away that last shirt for an 11th loaf of bread. The rate at which you are willing to substitute one good for the other diminishes. Hence, the curve flattens out, creating that convex bow shape.
Variety is the spice of life, basically translated into geometry. But the IES examiners rarely just give you a simple, well-behaved convex curve. They want to test if you understand the boundary conditions, the edge cases. So let's walk through these. What happens if the two goods in question are perfect substitutes?
Well, if goods are perfect substitutes, imagine two identical brands of bottled water or, exchanging a $10 bill for two $5 bills. The consumer is always willing to trade them at a constant, unchanging rate, regardless of how much of either they currently possess.
So the marginal rate of substitution does not diminish at all.
Correct. It is a constant. Therefore, the indifference curve is not bowed. It is a perfectly straight, downward-sloping line.
Okay, flip it to the other extreme. Perfect complements. Goods that are absolutely useless unless consumed together in a fixed, rigid ratio. The classic example is a left shoe and a right shoe.
Right. For perfect complements, having 5 left shoes and 1 right shoe Gives you the exact same utility as having one left shoe and one right shoe. You still only have one functional pair. The 4 extra left shoes add literally 0 marginal utility.
Visually, that creates an L-shaped indifference curve, correct? Like a sharp right angle.
Yes. The point of EL, the kink, represents the optimal fixed ratio, one left shoe, one right shoe. Moving horizontally or vertically away from that kink just means you are piling up useless inventory of one good without increasing your utility one bit. You cannot reach a higher utility level until you acquire more of both goods in the correct proportion.
Okay, what if the examiner throws a trick question where one of the commodities is actually something you hate, a bad? Let's say we're looking at a job contract. The horizontal axis is your income, which is a good, but the vertical axis is the risk of physical injury, which is a bad.
This really tests your fundamental understanding of what an indifference curve represents. Constant utility. If I force you to take on more of the bad, more risk of injury, your utility plummets. To keep you on the same indifference curve, to restore your utility to its original level, I must compensate you.
I need a bribe. I need more of the good commodity.
Exactly. You require more income. Therefore, as risk increases, income must increase simultaneously to keep you indifferent. This means the indifference curve is actually upward sloping. It slopes up and to the right. Higher utility is achieved by shifting the entire curve toward the axis of the good commodity and away from the bad.
Makes perfect sense. And finally, what if one commodity is completely neutral? It gives you 0 utility, but it doesn't hurt you either. Let's say the horizontal axis is pizza, and the vertical axis is the number of paper clips sitting on my desk.
If paper clips are entirely neutral, your utility is solely a function of pizza. If I dump 1,000 paper clips on your desk, your happiness doesn't change. You remain exactly where you are in terms of utility.
So the curve is just a vertical line shooting straight up from the pizza axis. Adding paper clips moves me vertically up the line, but I haven't moved to a new utility curve. I only get happier if I move to the right, getting more pizza.
Precisely. If the neutral good is on the y-axis, the indifference curves are vertical lines. If the neutral good is on the x-axis, they are perfectly horizontal lines.
We keep referring to this rate of trading. We need to formalize this because it is the exact target of the 2025 IES PYQ, the marginal rate of substitution, or MRS.
Right. So the MRS is the slope of the indifference curve at any specific tangent point. It measures the maximum amount of one good a consumer is willing to sacrifice to obtain one infinitesimally small additional unit of another good while keeping their total utility strictly constant.
Let's translate the calculus into plain English for the listener.
Sure. Mathematically, the marginal rate of substitution of good X for good Y is equal to the negative ratio of their marginal utilities. That is, MRS equals the negative marginal utility of X divided by the marginal utility of Y.
Why is there a negative sign there?
Because it's a trade-off. To move along the curve and get more of X, you must inherently subtract or give up some quantity of Y. So the slope is naturally negative.
Let's tackle that 2025 PYQ directly. The examiner asks you to calculate the exact MRS for a Cobb-Douglas utility function. Cobb-Douglas is basically everywhere in microeconomics.
Oh, it is the bedrock functional form. The question will define utility as U equals the quantity of good X raised to the power of alpha, multiplied by the quantity of good Y raised to the power of beta.
Okay, when you see that on the exam paper, what is your exact first step?
You need to isolate the marginal utilities.
Yeah.
And you do this by taking partial derivatives. So the marginal utility X is just the partial derivative of the utility function with respect to X.
And crucially, when taking a partial derivative with respect to X, we treat the quantity of Y as a fixed constant, ceteris paribus, all else equal.
Exactly. Applying the standard power rule of differentiation, you bring down the exponent alpha. So the marginal utility of X becomes alpha multiplied by X raised to the power of alpha minus 1 multiplied by Y raised to the power of beta.
Got it. That is the numerator of our MRS formula. Now we need the denominator, the marginal utility of Y.
We just repeat the process. Take the partial derivative of the utility function with respect to Y, treating X as a constant this time. Bring down the exponent beta. This yields beta multiplied by X raised to the power of alpha multiplied by Y raised to the power of beta minus 1.
Okay, now we stack them to find the MRS negative mu of X divided by mu of Y. We have this massive fraction with alpha, beta, X, and Y terms everywhere. How does it simplify?
It simplifies beautifully through the basic rules of exponents. Look at the x terms first. You have x to the power of alpha minus 1 in the numerator and x to the power of alpha in the denominator. When you divide, you subtract the exponents. Alpha minus 1 minus alpha leaves you with x to the power of negative 1, which simply moves x to the denominator.
And the y terms just do the reverse. You have y to the power of beta in the numerator and y to the power of beta minus 1 in the denominator. That leaves a single y in the numerator.
Exactly. Therefore, the entire messy fraction collapses. The final, simplified answer for the 2025 PYQ is the marginal rate of substitution is equal to negative alpha times y, all divided by beta times x.
Negative alpha y over beta x. That is your 5-mark answer right there. But let's pause for a second. What does that actually tell us economically? Like, why is Cobb-Douglas so elegant?
Because those parameters, alpha and beta, represent the relative intensity of the consumer's preference for the two goods. In a Cobb-Douglas world, the MRS is directly proportional to the ratio of the quantities consumed, scaled by those preference parameters. It actually implies the consumer will ultimately spend a constant fraction of their income on each good, determined entirely by the ratio of alpha to beta.
That is brilliant. It mathematically locks in their budget shares. But, speaking of budgets, having a beautifully mapped out mind full of indifference curves doesn't mean you can just walk into a store and take whatever you want.
Yeah.
We have to introduce objective reality.
We must introduce the budget constraint. This represents the cold, hard limits of reality. It defines all the combinations of goods a consumer can actually afford, given their fixed nominal income and the prevailing market prices of the goods.
Visually, it is a straight, downward-sloping line slicing across the graph. And the slope of that budget line is the negative ratio of the market prices. Negative price of X divided by the price of Y.
This ratio is critical. It represents the rate at which the market allows you to physically trade one good for another. Like if coffee is $5 and a sandwich is $10, the market exchange rate is 2 coffees for 1 sandwich. The market does not care about your utility or your preferences. The market only cares about prices.
So now we have 2 competing forces. We have the slope of the indifference curve, the MRS, which is your subjective internal valuation, and we have the slope of the budget line, the price ratio, which is the objective external market valuation. How do these 2 forces actually resolve?
They resolve at consumer equilibrium. The rational consumer wants to reach the highest possible indifference curve, the highest state of utility. But they are trapped behind the wall of their budget line. They just cannot afford anything beyond it.
So they push as far out as they can until they just barely touch the highest affordable curve?
Exactly. Utility is mathematically maximized at the precise point where the budget line is perfectly tangent to the highest attainable indifference curve.
Let's translate that tangency condition for the exam.
At the point of tangency, 2 curves share the exact same slope. Therefore, utility is maximized where the marginal rate of substitution equals the negative ratio of the prices. Specifically, the marginal utility of X divided by the marginal utility of Y exactly equals the price of X divided by the price of Y.
Let's look at the intuition behind this formula because it's pretty profound. If I rearrange it algebraically, it says that the marginal utility of X divided by its price must equal the marginal utility of Y divided by its price.
Yes, that's the famous equimarginal principle.
Which means the last dollar I spend on coffee must bring me the exact same amount of happiness as the last dollar I spent on a sandwich. Because if coffee gave me more bang for my buck, more utility per dollar, I would just shift my spending, right? I'd buy more coffee and fewer sandwiches.
And as you buy more coffee, the law of diminishing marginal utility kicks in.
Yeah.
The marginal utility of coffee drops. And as you buy fewer sandwiches, the marginal utility of sandwiches rises. You keep adjusting your basket until the utility per dollar is perfectly equalized across all goods.
Once that equalizes, my internal exchange rate perfectly matches the supermarket's exchange rate. I am at peace. I am at equilibrium. No possible reallocation of my budget could squeeze out even one more drop of happiness.
That is the absolute pinnacle of the static consumer model.
Okay. We have built the consumer. We gave them a budget. They found their perfect equilibrium. Now, we are going to ruin their day. We are going to shock the system. We are going to change the price of a good and watch the mathematical chaos unfold. This brings us directly to the mechanics behind the 2024 PYQ, price effects and Slutsky's theorem.
Right. When a market price changes, say the price of X falls, it appears to be a single event. But economically, it is actually 2 completely distinct simultaneous shocks to the consumer's reality. We call the final total outcome the price effect. But to truly understand demand, we must mathematically decompose it.
Let's say the price of coffee drops from $5 to $4. First, coffee is now cheaper relative to sandwiches. The exchange rate of the market has shifted. This triggers the substitution effect.
The substitution effect is the consumer's natural reaction to a change in relative prices, isolating that specific change. Because coffee is now relatively cheaper, a rational consumer will substitute away from the relatively more expensive sandwiches and buy more of the relatively cheaper coffee.
And the substitution effect is always strictly negative with respect to price, correct? Meaning price and quantity demanded move in opposite directions. Price goes down, substitution drives quantity up.
Always. But there was a second hidden shockwave. Because coffee is cheaper and you are already buying coffee, you now have leftover money in your budget. It is as if your paycheck magically increased. Your nominal income hasn't changed, but your real purchasing power has expanded.
My money basically goes further. I am functionally richer.
This is the income effect. And the income effect is where all the complexity lives. The direction of the income effect depends entirely on the nature of the good. If coffee is a normal good, feeling richer makes you want to buy more of it.
So for a normal good, the income effect pushes in the exact same direction as the substitution effect. They team up. Both forces command you to buy more coffee.
But what if it is an inferior good, say instant noodles? When your real purchasing power goes up, when you feel richer, you actually buy less instant noodles. You upgrade your diet to fresh pasta.
So for an inferior good, the income effect actively fights against the substitution effect. Substitution says it's cheaper, buy more. Income effect says you're richer, buy less.
Exactly. And to analyze this mathematically and prove demand curves, we have to artificially separate these two intertwined effects. We have to figure out a way to hold one variable constant while we change the other. Historically, there are two legendary methods for this decomposition: the Hicksian approach and the Slutskian approach.
Let's break down the theoretical difference because examiners just love testing this nuance. How did John Hicks decompose the price effect?
Well, Hicks wanted to isolate the pure substitution effect by holding the consumer's psychological welfare constant. In the Hicksian approach, when the price of coffee falls, making the consumer functionally richer, we hypothetically act as a tax collector. We reach into their pocket and confiscate just enough of their income so that, facing the new lower prices, they are forced back down to their original indifference curve.
We strip away their newfound purchasing power until they are exactly as happy as they were yesterday. No happier, no sadder.
Yes.
Yeah.
They are locked onto the same utility curve, but they are now facing the new, flatter slope of the new price ratio. So they must move along that original curve to find a new point of tangency. That specific slide along the same curve is the Hicksian substitution effect.
Okay, that is super elegant. But what did Eugen Slutsky do differently?
Slutsky took a much more empirical, observable approach. He didn't really care about the invisible psychological curve of utility. He cared about observable purchasing power. In the Slutskian decomposition, when the price falls, we hypothetically confiscate just enough income so that the consumer can just barely afford their original consumption bundle.
Oh, I see the distinction. Hicks says you can be just as happy. Slutsky says you have exactly enough cash to buy the exact same shopping cart of groceries you bought yesterday.
Precisely. We give them enough money to buy the old bundle at the new prices. But here is the absolute genius of Slutsky. Because relative prices have changed, even though they can afford the old bundle, they won't choose it. They will optimize, they will substitute toward the cheaper good, and in doing so, they actually manage to reach a slightly higher indifference curve than they started on.
So the Slutsky compensation is actually a little bit more generous than the Hicksian compensation. The consumer ends up slightly better off.
Which leads us to the mathematical crown jewel, the formal Slutsky equation. This equation literally bridges the gap between everyday, uncompensated demand and theoretically pure compensated demand.
Let's translate the calculus of the Slutsky equation for the listener.
The Slutsky equation states that the total rate of change in demand due to a price change is the sum of the substitution rate and the income rate. Mathematically, the partial derivative of ordinary Marshallian demand with respect to price equals the partial derivative of compensated Hicksian demand with respect to price minus the initial quantity consumed of the good multiplied by the partial derivative of ordinary Marshallian demand with respect to income.
Let me repeat that slowly so the structure is crystal clear. The total effect on demand equals the substitution effect, which is the compensated derivative, minus the income effect. And the income effect is composed of two parts multiplied together. The raw quantity of the good you already buy, multiplied by how sensitive your demand is to a change in income.
Yes, and that multiplication by the initial quantity consumed is the secret to everything. It determines the sheer magnitude of the income shock.
Let's use a real-world example to clarify that. If the price of my monthly rent goes up by 10%, The income effect absolutely destroys my purchasing power because rent is a massive quantity of my budget. I feel incredibly poor. But if the price of toothpicks goes up by 10%, the income effect is mathematically practically zero because the initial quantity consumed in my budget is infinitesimal.
That is a perfect explanation. The income effect is heavily weighted by the budget share of the good. And this exact mechanic is what explains the 2024 PYQ, the derivation of the given good.
Let's go back to our opening hook, the paradox where price goes up and people buy more. How does the Slutsky equation mathematically prove that a given good can actually exist?
Well, a given good requires two extreme simultaneous conditions to be met within the Slutsky framework. First, the good must be deeply inferior. This means the partial derivative of demand with respect to income is highly negative. As you get richer, you buy much less. As you get poorer, you buy much more.
Condition 1, deeply inferior good.
Got it. Condition 2, it must consume a massive, overwhelming portion of the consumer's total budget.
Okay, let's look at the classic, somewhat debated historical example. Potatoes during the Irish potato famine. Or, in a modern context, imagine a family living in extreme poverty where 90% of their daily budget goes strictly to cheap rice just to meet basic caloric needs, and maybe 10% goes to a tiny bit of chicken.
Right. Now, a devastating drought hits. The price of rice skyrockets.
Let's run it through the Slutsky equation. First, the substitution effect. Rice is now more expensive relative to chicken. The substitution effect is negative, so it commands the family to buy less rice and buy more chicken.
But look at the income effect. Because rice made up 90% of their budget, the price increase in rice is essentially a catastrophic destruction of their real income. They are now functionally destitute.
And because rice is an inferior good, it's the cheap calorie source. What do you do when you are completely destitute? You cannot afford the chicken at all anymore. You have to drop the luxury item entirely just to survive.
Exactly. You take the money you used to spend on chicken, and you are forced to spend it on more of the expensive rice just to avoid starvation. The positive push of the income effect, forcing you to buy more of the inferior good because you are poorer, is mathematically so massive that it completely overwhelms the negative pull of the substitution effect.
So the substitution effect says, buy 2 less bowls of rice. The income effect says, you are so poor, you must buy 5 more bowls of rice to survive. Net total price effect. You buy 3 more bowls of rice, even though the price went up.
And if you plot that on a standard graph, with price on the vertical axis and quantity on the horizontal axis, you do not get a downward sloping line. You get an upward sloping demand curve. The demand curve physically bends backward.
That is wild, and that is why it is such an important exam question. It proves that demand is not a psychological absolute. It is a mathematical consequence of purchasing power.
Now that we understand how these equilibrium points shift when prices change, we can actually map those shifts to derive our standard demand curves.
Right. Moving from the microscopic world of tangency points to the macroscopic world of market demand.
If we hold a consumer's nominal income strictly constant, and we just incrementally lower the price of good X, the budget line will pivot outward, becoming flatter. With each pivot, it will touch a new, higher indifference curve. If we draw a line connecting all those sequential equilibrium tangency points across the indifference map, we trace out the price consumption curve, or PCC.
The PCC is basically the breadcrumb trail of optimal choices as the price falls.
And it contains all the raw data we need to build the demand curve. If we simply extract the price from the slope of the budget line and the optimal quantity from the tangency point and plot them against each other on a new graph, we have derived the ordinary demand curve.
What if we run the other experiment? We hold prices absolutely constant so the slope of the budget line never changes. But we continuously increase the consumer's income. The budget line doesn't pivot, it shifts outward in parallel.
If we connect those tangent equilibrium points as income shifts, we trace the income consumption curve, or ICC.
And if we plot the data from the ICC plotting income on the vertical axis against quantity demanded on the horizontal axis, we get the angle curve. The angle curve is incredibly useful because its slope instantly tells you the nature of the good. If it slopes upward, the good is normal. If it bends backward and slopes downward, the good is inferior.
This leads us to a crucial distinction you must clarify for the examiner. We have been discussing two very different realities of demand: ordinary demand versus compensated demand.
Right. Ordinary demand, or Marshallian demand, is the standard textbook curve. It plots the total raw reaction to a price change.
Which means the ordinary demand curve explicitly contains both the substitution effect and the income effect all rolled into one.
But compensated demand, or Hicksian demand, is a purely theoretical construct. It is the demand curve that would exist if a benevolent dictator magically adjusted your income every single time a price changed, ensuring your utility remained perfectly constant.
Therefore, the compensated demand curve strips out the income effect entirely. It isolates and reflects only the pure substitution effect. Because it lacks the extra momentum of the income effect, the compensated demand curve for a normal good is always steeper, meaning it is less elastic, less responsive than the ordinary demand curve.
Because ordinary demand is flatter, because the income effect acts as an amplifier. If the price drops, substitution says buy more, and the income effect says you're richer, buy even more.
Precisely. Now, before we move to the math of duality, there is a fundamental mathematical property of ordinary Marshallian demand functions that the IES exam loves to test as a trap. It's called homogeneity of degree zero.
Homogeneity of degree zero. It sounds pretty intimidating, but the intuition is actually fascinating. Let's translate this.
The property states that ordinary demand functions are homogeneous of degree zero with respect to prices and income. This means if you multiply every single price in the economy and your total nominal income by the exact same positive constant k, the optimal quantities you demand will not change by a single fraction. Mathematically, demand as a function of prices and income, d of p and m, is perfectly equal to demand as a function of k times prices and k times income, d of kp and k and m.
I have an analogy for this. Let's say a bizarre economic shock hits tomorrow. Hyperinflation overnight. The price of absolutely everything in the supermarket, coffee, bread, cars, rent, exactly doubles. The constant K is 2.
The severe shock.
But on that exact same morning, your employer calls and says, due to the inflation, we're instantly doubling your paycheck. So your income is also multiplied by 2. When you walk into the supermarket that afternoon, do you change your shopping habits?
You do not change a thing because the relative prices, the ratio of the price of coffee to the price of bread, have not changed. And your real purchasing power, the physical amount of goods your new paycheck can buy, is identical to yesterday.
So my demand function cancels out the K. I do not suffer from what economists call money illusion. I don't panic when I see the price of coffee is $10 instead of $5 because I intuitively know my income scaled perfectly to match.
And that is exactly how the examiner will test you. They will give you a messy algebraic demand function and ask you to prove it is free of money illusion. You simply substitute k times p for every price p and k times m for income m. If you can factor out the k entirely, proving the equation remains unchanged, you have proven it is homogeneous of degree 0.
That is a great exam tip. All right, we have built this incredible model by maximizing utility subject to a budget constraint. We took a pile of money and squeezed the maximum possible happiness out of it. We call this the primal problem. But what if we reverse engineer the entire universe? What if we look at the exact same problem from the other side of the mirror?
This brings us to duality theory. It is arguably the most mathematically elegant concept in all of microeconomics. Duality states that maximizing utility for a given budget is mathematically structurally identical to minimizing your expenditure to reach a specific target utility level.
I want to use a translation analogy here. If the primal problem is writing a complex sentence in English, the dual problem is writing the exact same meaning perfectly in French.
That is a highly accurate way to frame it. The primal problem asks, here is exactly $100. Optimize your basket to make yourself as happy as mathematically possible.
And the dual problem asks, I want you to achieve exactly 50 utils of happiness today. I don't care how you do it, but you must reach that target by spending the absolute minimum amount of money possible.
If you solve both Lagrangian maximization and minimization problems, the optimal final bundle of goods you walk out of the store with is exactly the same in both scenarios. They're two sides of the identical coin.
And realizing this duality unlocks two incredibly powerful new mathematical functions. Up until now, we've only talked about the direct utility function, where you plug in the physical quantities of goods, and it spits out your utility level.
But duality gives us the indirect utility function. Instead of physical quantities, you plug in market prices and your total income. And the function spits out the maximum possible utility you could achieve given those market conditions. We denote it as V of P and M. It evaluates the consumer's welfare indirectly, looking only at the market constraints they face.
Okay, that is the primal side translated. What about the dual side?
That gives us the expenditure function, denoted as E of P and U. Here, You plug in market prices and a target utility level, and it calculates the minimum amount of money required to reach that level of happiness at those specific prices.
So the indirect utility function turns money into maximum happiness. The expenditure function turns a happiness target into minimum money required. They are exact mathematical inverses of each other.
They are. And because they're so structurally perfect, they provide us with profound shortcuts. Think of them as the dictionary that lets you instantly translate between the English of the primal problem and the French of the dual problem without having to painstakingly rewrite the entire Lagrangian calculus every single
I
time.
love a mathematical shortcut. Let's talk about the first dictionary translation, Roy's identity. How do we extract an ordinary demand curve from the indirect utility function?
Roy's identity states that you can derive the ordinary Marshallian demand function for a specific good through a simple ratio of partial derivatives. The formula is, take the partial derivative of the indirect utility function with respect to the price of the good. Then, divide that entirely by the partial derivative of the indirect utility function with respect to income. Finally, multiply the result by -1.
Let's explain the why behind that ratio. Why are we dividing the price derivative by the income derivative?
Think about the rates of change. The numerator asks, if the price of coffee goes up by $1, how much does my total maximum happiness drop? The denominator asks, if my income goes up by $1, how much does my happiness increase? By dividing the two, you are essentially asking how much extra income would I need to exactly buy back the happiness I just lost to the price hike.
And the answer to that question, the amount of money required to offset the price change, is exactly equal to the physical quantity of the good you are currently demanding. It is a brilliant way to normalize subjective utility back into objective, observable quantities.
Exactly. And the second translation tool is Shepard's lemma. This operates on the dual side, using the expenditure function, and it is even more elegant.
What is the calculus for Shepard's lemma?
Shepard's lemma states, take the partial derivative of the expenditure function with respect to the price of a specific good. That is the entire operation. The result of that single derivative is exactly the compensated Hicksian demand function for that good.
You just differentiate the minimum cost function by the price of coffee, and it instantly reveals exactly how much coffee you need to buy to maintain your utility target. Why does that work so simply?
Because of the envelope theorem. If you are already minimizing your costs perfectly, a tiny increase in the price of coffee only increases your total expenditure by the exact amount of coffee you are currently buying. You don't have room to substitute yet. So the rate of change of your total cost is exactly equal to your current demand.
That is incredibly powerful. These tools are the foundation of modern cost of living indices and government tax policy evaluation because they let economists calculate exactly how much money people need to maintain their standard of living when inflation hits.
Now, I need to pivot our entire framework. We have spent the last 15 minutes building an elaborate, beautiful mathematical castle. But that entire castle rests on a single massive assumption, that we know what utility is, that we can confidently draw indifference curves in a consumer's brain.
We are assuming we know what is going on inside the black box of human psychology.
But what if we can't? What if utility is a total fiction, an unobservable ghost in the machine? What if we are modeling something that doesn't physically exist?
This sounds like an existential crisis for microeconomics.
It was, until Paul Samuelson introduced revealed preference theory in 1938. This theory is the specific focus of the 2023 PYQ. Samuelson argued that we need to throw the psychology out the window. We don't need to ask people to rank hypothetical bundles of goods. We just need to watch what they actually do in reality.
Actions speak louder than utility functions.
Precisely. Samuelson said that if we observe a consumer's choices at the cash register under different shifting budget constraints, different prices, and different incomes, we can deduce everything we need to know about their preferences just by tracking their behavior.
And this empirical approach rests on two massive foundational axioms. The first is warp, the weak axiom of revealed preference.
Warp is the fundamental test of behavioral consistency. The rule dictates, if a consumer chooses bundle A, when bundle B is also perfectly affordable and sitting right there on the shelf, the consumer has definitively revealed a strict preference for A over B.
Okay, that makes sense. I bought the coffee when I had enough money in my pocket to buy the tea. Therefore, my action reveals I prefer coffee.
The axiom then states that if you have revealed A is preferred to B, you can never be observed choosing bundle B in the future under any price conditions as long as bundle A is still affordable.
I am going to push back on this because it feels a little rigid for human beings. What if I buy the coffee on Monday, but on Tuesday I just want variety? I still have enough money for coffee, but I buy the tea just because I'm bored. According to Warp, I am acting irrationally. Doesn't this mathematical axiom completely ignore the reality that humans get bored?
It does ignore boredom, and that is a perfectly valid psychological critique. But remember the goal. We are trying to build a predictive mathematical model of demand. If preferences change daily on a whim, if you buy A over B today and B over A tomorrow purely for variety, then your preferences are fundamentally unstable. You cannot draw a static indifference curve, and the entire math of demand collapses. Warp strictly assumes your underlying preferences are fixed over the period of observation.
Right. If I prefer coffee to tea, the only mathematically acceptable reason for me to switch and buy the tea is if the price of coffee skyrocketed so high that I literally cannot afford bundle A anymore. If I can afford both and I switch, I violate Warp. My data is corrupted.
Exactly. Warp guarantees that a consumer's choice avoids direct, immediate contradiction. But to prove that demand theory works entirely without utility, to ensure the whole system is logically sound, avoiding direct contradiction isn't enough. We must avoid circular contradictions.
Which brings us to the second pillar, SARP, the strong axiom of revealed preference. What does SARP add to the foundation that Warp missed?
SARP adds the mathematical requirement of transitivity across a chain of multiple choices. Warp only looks at two bundles at a time. It compares A directly to B. SARP looks at the entire sequence.
Give me the chain.
If you reveal a preference for bundle A over bundle B in January, and then under new prices in February, you reveal a preference for bundle B over bundle C.
Then logically, I must prefer bundle A over bundle C.
Yes. SARP states that if A is revealed preferred to B and B is revealed preferred to C, then you can never choose C in the future if A is affordable. If you do choose C when you could have bought A, you have created an irrational circular loop. A beats B, B beats C, C beats A.
It's like playing rock, paper, scissors with your groceries. You can't build a hierarchy if paper beats rock, rock beats scissors, and scissors beat paper. There is no top tier.
And here's the crowning mathematical achievement of SARP. Samuelson and others proved that if a consumer's observed empirical behavior consistently satisfies the strong axiom of revealed preference over enough price changes, we can mathematically work backward to construct their entire set of indifference curves.
Wait, really? We can draw the curves without ever asking them what they feel?
Yes, we can map the invisible psychology using only the hard empirical data of cash register receipts. We just plot every bundle they ever chose, shade in the areas of bundles they rejected, and the boundaries that form will perfectly trace out their indifference curves.
That is mind-blowing. It completely bridges the gap between pure behavioral observation and complex theoretical math. And that is exactly why the 2023 PYQ asks you to check the consistency of a consumer's behavior.
Yes, the examiner will give you a logic puzzle, a data table showing prices and quantities in period 1 and new prices and quantities in period 2.
How do you solve it?
You have to act as an auditor. You calculate the cost of the period 1 bundle using period 1 prices. Then you calculate what the period 2 bundle would have cost at period 1 prices. If the period 2 bundle was cheaper, meaning it was affordable in period 1 but they chose bundle 1 instead, they have revealed a preference for bundle 1. You then run the exact same test in reverse for period 2. If they ever buy B when A was affordable, after previously choosing A, you write down violation of Warp and collect your marks.
You are literally auditing their rationality. That's fantastic. All right, we are entering the final toolkit. To fully analyze demand for the IES exam, we have to be able to measure how aggressively demand reacts to changes and what happens to the consumer's overall welfare in the market.
We measure responsiveness using elasticities. There are 3 core metrics. First, the price elasticity of demand. This measures the percentage change in the quantity demanded of a good change, resulting from a 1% change in its own price. Because of the law of demand, this number is almost always negative.
Second is income elasticity. This measures the percentage change in quantity demanded resulting from a 1% change in the consumer's income. This is how we mathematically classify goods. If the elasticity is positive, it is a normal good. If it is negative, it is an inferior good. If it is positive and greater than 1, meaning demand grows faster than income, it is a luxury good.
And the third is cross-elasticity. This measures how the quantity demanded of good X reacts when the price of a completely different good Y changes by 1%.
This defines substitutes and complements, correct?
Yes. If the cross-elasticity is positive, meaning the price of tea goes up, so you buy more coffee, they are gross substitutes. If the cross-elasticity is negative, meaning the price of coffee goes up, so you buy less sugar, They are gross complements.
Why do economists specify the word gross in front of substitutes and complements?
Because we have to remember Slutsky. A price change inherently contains both a substitution effect and an income effect. Gross elasticity measures the total, ordinary, real-world reaction, mixing both effects together. In some extreme mathematical cases, a bizarre income effect can overpower the substitution effect and make two goods look like complements when they are actually substitutes. But for the standard IES exam questions, just remember, positive cross-elasticity means substitutes, negative means complements.
Got it. Now, the final piece of the puzzle. Welfare. How do we measure the actual tangible benefit a consumer gets from participating in a market? How do we measure the value of trade?
We use the concept of consumer surplus. Strictly defined, consumer surplus is the monetary difference between the absolute maximum amount a consumer was willing to pay for a specific quantity of a good and the amount they actually did pay at the market price.
Geometrically, if you draw a standard supply and demand graph, consumer surplus is the triangular area strictly below the downward-sloping ordinary Marshallian demand curve and strictly above the horizontal market price line up to the total quantity purchased.
It represents the extra uncharged utility you walked away with. If you were starving and willing to pay $10 for a sandwich, but the market price is only $3, you gained $7 of pure surplus value. The market made you richer in utility.
And this is why taxes and monopolies are studied so heavily. If a monopoly raises the price from $3 to $6, that horizontal price line moves up, and the triangular area of your consumer surplus shrinks drastically.
And crucially, some of that lost surplus is not captured by anyone. It doesn't go to the government as tax revenue, and it doesn't go to the monopoly as profit. Because the price is higher, some people simply stop buying the sandwich. Those mutually beneficial trades are destroyed. That vanished, evaporated surplus is called deadweight loss. It is a pure, unrecoverable destruction of economic efficiency and human welfare.
That is a stark reality to end on. We have covered an immense amount of ground today. We started inside the mind, debating whether utility is a cardinal absolute or an ordinal ranking, settling on the elegance of indifference curves and the marginal rate of substitution.
We constrained the consumer with a budget, finding their equilibrium at the exact point of tangency where their subjective desires perfectly matched objective market prices.
We shocked that equilibrium using Hicks and Slutsky to decompose price changes into substitution and income effects, unraveling the extreme mathematics of the Giffen-Good paradox.
We use those shifting equilibria to trace out price consumption and income consumption curves, deriving ordinary and compensated demand, and proving the absence of money illusion through homogeneity of degree zero.
We flipped the entire mathematical universe to explore duality, translating the primal problem into indirect utility and expenditure functions, and using Roy's identity and Shepard's lemma as our dictionary keys.
And finally, we abandoned psychology altogether, proving with revealed preference theory that we can audit a consumer's rationality and rebuild their indifference map using nothing but cash register receipts and the axioms of Warp and SARP, before tying it all back to the real-world metric of consumer surplus.
Now, for the ultimate payoff for you, the listener, let's do some exam forecasting. Based on the deep analysis of the syllabus and these historical PYQs, what are the 3 most likely question patterns they will face in the IES 2026 GE-01 exam regarding consumer demand?
If I were setting the paper, I would heavily test the intersection of the math and the intuition. First pattern, derive compensated demand from a given utility function. They will hand you a Cobb-Douglas or CES utility function. Do not use the Lagrangian to find ordinary demand. Set up the dual problem. Minimize expenditure subject to the target utility, find the expenditure function, and immediately apply Shepard's lemma. It tests duality and derivatives in one swift move.
Duality and Shepard's lemma, that is high-level execution. What is the second pattern?
Second, Slutsky decomposition with actual numerical values. They will not just ask for the theory. They will give you an initial price of $10, an income of $100, and a price drop to $8. You will have to calculate the exact numerical split, how many units of demand change strictly due to the substitution effect, and how many strictly due to the income effect. You must know how to artificially adjust the income M in the demand function to hold purchasing power constant.
You have to be able to crunch the actual Slutsky compensation. And the third?
Third, a revealed preference consistency check, exactly like the 2023 PYQ. It will be a pure logic puzzle, a matrix of prices and quantities across 2 or 3 periods. You must methodically calculate the cross-period costs and explicitly document whether the consumer violated Warp or SARP. It is tedious, but it proves you understand the empirical foundation of the theory.
Audit their grocery receipts and prove their rationality. That is an incredibly powerful roadmap for revision.
It covers the theory, the calculus, and the empirical application perfectly.
As you head back to your textbooks and your partial derivatives, I want to leave you with one final provocative thought. We just spent an hour building this breathtakingly perfect mathematical architecture. The entire edifice, from Hicksian compensation to duality to revealed preference, assumes that consumers are highly rational, fiercely consistent, utility-maximizing machines. It relies entirely on the premise that what you choose at the cash register is definitively what is best for you.
It assumes absolute behavioral perfection.
But think about human reality. How does this beautiful math handle a consumer who makes a profound mistake? The person who buys an expensive piece of exercise equipment on an impulsive whim at 2 a.m., never uses it once, and deeply regrets the purchase the next morning. According to revealed preference, they revealed a preference for the treadmill over keeping their cash. But did that choice actually maximize their utility? Or is the rationality we rely on just an illusion created by the mathematics of demand, deliberately ignoring the messy, irrational reality of human regret?
It is the ghost that haunts the entire neoclassical model.
Yeah.
Are we modeling humans, or are we just modeling algorithms?
Ponder that structural flaw as you master the equations. Good luck on the GE-01 exam. We will see you on the next deep dive.